So in the appendix, I want to show that the Dirac Hamiltonian has eigenvalues plus EP, EP, and minus EP and EP. So what is the Dirac Hamiltonian? The Dirac Hamiltonian is C alpha dot P plus M C squared beta. So first we're going to show that it's traceless. So it's traceless. That is, if I take the matrix trace of H, then is 0. That means that its eigenvalues come in pairs. If it has an eigenvalue, say A, it should also have an eigenvalue minus A. So to do this, all we have to show is that the matrix alphas and beta are traceless. So let's look at the tracelessness of B. So beta, so trace of beta is equal to trace of, say, alpha 1 squared times beta, where we've used the fact that alpha I, alpha j, the anti-commutator is 2, delta ij. So if I put I and j equals to 1, I get 2, alpha 1 squared is 2. And therefore we can, alpha 1 squared is 1. So we can insert alpha squared here. And then what we can do is that we can use the fact that the trace is cyclic to write this as alpha 1, beta, alpha 1. But we can also use the fact that alpha and beta anti-commute to write this first line as minus trace of alpha 1, beta, alpha 1. And therefore, we see that this is equal to its own negative of itself. And therefore, trace of beta is 0. So similarly, we can prove all the alpha are traceless because trace of alpha 1 can be written as, you guessed it, trace of alpha 1 times beta squared, because beta squared is also 1, and then we can use the cyclicity of the trace to write this as beta alpha 1 beta. And then, of course, this can be written using the anti-commutation relationship as minus trace of beta alpha 1 beta, and therefore this is equal to 0. So now suppose, so we have shown that H is traceless, but we know that H squared is given by C squared P squared plus M squared C4. And therefore the possible eigenvalues of H are plus minus this thing, which is EP. Therefore we have shown that the eigenvalues of H are plus EP or minus EP, and they occur in pairs.